Okay, let's talk about differential equations. We'll look first at these things called population growth models. This is a really good place to start with differential equations because it introduces one of the simplest sort of actual differential equation models. And when you take that class, what you'll probably start with is the idea of how do you make a model, a mathematical model that's going to accurately portray something that's happening. And in this case, population growth is something that we want to model, right? Like how fast is the population of this city growing or the country or whatever. And in order to come up with these models, what you have to do is you have to make a couple of assumptions, right? And any model, you have to make assumptions with them, right? And so the assumptions that come with this population growth model are very simple. What is the assumptions that we make when we're coming up with a model like this? Well, the first assumption is that the rate of growth of the population, in fact, this is the only assumption we need for this one, the rate of growth of a population is proportional to the size of the population, or even just the population itself. Maybe just to be clear about that, maybe I should say the size of the population. Okay, so again, that's a pretty simple assumption, and but it's also a good assumption to make if you think about it, right? Like if you think about the way that algae, or maybe not algae, but like bacteria grows on a petri dish, if you think about the way that it first starts to grow, like if you've seen a time lapse of that kind of thing, right away it doesn't really grow very fast because there's not much bacteria on there, right? And so the rate of growth is pretty slow. But as the population gets bigger, you'll notice that it really spreads out a lot faster as it gets bigger and bigger, right? And so the rate of growth, the bigger it is, the faster it grows, is basically what that's saying. And so even with this one assumption, this pretty simple assumption, we can come up with a differential equation. In fact, we can translate this sentence directly into an equation. So how do we do that? Well, let's see. The rate of growth, okay, just what does that mean? Rate of growth. Well, as soon as you see that word rate, we should be thinking about derivative. Yeah, exactly. Rate of growth is a derivative. And it's the rate of growth of a population, okay? And so if we assign a variable p to be population, and then time, t for time, then the rate of growth translates directly into dp dt. That's the rate of change of a population. Is, again, if you kind of think back to your intermediate algebra or college algebra, that the proportions, if you remember that, translating stuff into mathematical equations, is means equals. Is proportional to, what does that mean? Well, that introduces a constant of proportionality, okay? And so when you change this into a sentence, you get dp dt, again, is means equals, is proportional to, well, that's the constant of proportionality. We usually call that k. What is it proportional to? The size of the population. Well, we've said that the size of the population is denoted by a p. So that's it. This is a very simple differential equation. dp dt is equal to kp. Okay, and what is that saying? It's saying that the derivative of p, the derivative of p with respect to time, is proportional to p. K, again, is the constant of proportionality. If you, like I was saying, if you think back to your intermediate algebra class or your college, I can't remember which one they actually talk about that in. There was a section in there about proportionality, and they would do questions like this, but without rate of growth. It would just be like, this is directly proportional to that. This is inversely proportional to the square of that, right? And then you would make a mathematical equation about that. So anyway, that's what this is. Got to think back to that. So it's a constant of proportionality. K equals constant, and it's just the constant of proportionality. You could just call it a constant too. All right, so that's it. Very simple equation. And it says right there that any function of the form p of t is equal to c equals kt is a solution to this differential equation. So again, what is a differential equation then? What is a differential equation? Just looking at this, a differential equation, and it's really simple. What the definition is, just an equation That's it. That's the definition of a differential equation. So if you have any equation that has a function and one or more of its derivatives in this same equation, that's a differential equation. Okay. Okay. So in fact, in this case, I can actually show you how it says right there. This is the solution to that differential equation. A solution to this equation, as you can see there, it says that P of t is equal to C, that's a different constant, some other constant, e to the kt. So this is a solution to the differential equation. Well, what the heck does it mean to be a solution to the differential equation? You can note that in an algebraic equation, a solution is just a number, or numbers, perhaps more than one, right? Like if I give you an equation like this, 2x plus 5 is equal to 0, what's the solution to this equation? Well, you can quickly solve that and see that x equals negative 5 halves is the solution, right? That's an algebraic equation. What does the solution look like? It's just a number, right? This is just a number. And so what is the difference between that kind of equation and a differential equation? Well, look at the solution to the differential equation. What is this? It's clearly not a number. What is it? It's a function. So that's a huge difference between the types of equations that we are familiar with so far and this new type of equation called a differential equation. Rather than a number as a solution, you get a function as a solution. And you can see when you have a function as a solution, well, just like with a regular equation, how do you verify that it really is a solution? What do? You take this proposed solution, you plug it in for x, right? And then you verify that you do get, equality at the end of that, right? That's what it means to be a solution to an algebraic equation, that when you plug it in, you get a true statement at the end of that, okay? Well, the same thing is true about a differential equation. If we're claiming that this is a solution to it, then when I plug it into the differential equation, I should get a true statement. I should get equality, right? And so when we look at a differential equation, we see there's two halves to it, right? There's the left side and then there's the right side. You can even call them that left-hand side, right-hand side. And so when you want to verify that something is a solution, you just plug it in. And so what I would do to verify this is a solution is I would say, well, okay, let's see what happened. What do I get on the left-hand side if I plug that function in? Well, what is on the left-hand side? It's dp dt, which is the derivative of that, right? And so on the left-hand side, I need to know what is dp dt. Okay, well, what is dp dt? It's the derivative of p of t. So what's the derivative of that function? Well, it should be, according to our chain rule, it should be c times k e to the kt, right? That's the left-hand side. Everybody see why? I'm just taking the derivative. That's what dp dt is, okay? Right-hand side. What should I get on the right-hand side? On the right-hand side, I should get k times the function, right? That's what I see up here, right? K times p. Well, what's p? P is this right here. P is the function itself. So k times p should be k times c e to the kt. And now I just compare the two sides of this equation. Are these actually equal to each other? Is the left-hand side equal to the right-hand side? And you can tell clearly it is, right? Like all that's happening there is the c and the k have reversed, but multiplication is commutative, so these are definitely equal. Okay, everybody see kind of what we're doing to verify that we actually have a solution here? You just plug the proposed solution function into the differential equation. You have to plug it on the left side, plug it on the right side, verify that you have equality. Any questions about that? Now, this particular differential equation is simple enough that I can actually show you how we arrive at that solution. We have a solution, but it was just given to us. Well, why? Yeah, so we plug the function itself. That's right, we plug the function itself into both sides of the equation. The left side instructs us to take the derivative of the function, so that's what goes on the left side. On the right side, it instructs us to multiply the k times the function, okay? This is the function right here. That's it. So whenever I see a p, I'm going to just replace it with that. Whenever I see a dp dt, I'm going to replace it with the derivative of that, okay? So yes, you plug the function itself into both sides of the equation. Now let me show you how, yeah, no problem. let me show you how we would actually arrive at that solution. Again, because here in this case, all we did was we were just given it and said, okay, trust us, that's the solution. But in this case, like I said, this function is easy enough, simple enough that we can actually go ahead and solve it. So I'm going to show you how to solve this differential equation. It's done by a process called separation of variables, which we're actually going to talk more about in the next section, but might as well just introduce it right here. This is the only technique of solving differential equations that we're going to see in this class. There are about 3 other techniques that you will see in differential equations. One, let's see, it's called the method of the integrating factor. There's one. The method of variation of parameters. Everybody watches Futurama. Maybe you've heard that one. The math nerd, sci-fi, Simpsons type comment or cartoon, right? Separation of variables. Let's see, variation of parameters, and then what's the other one, Michael? The undetermined coefficient. That's the other one. And I think there's more.
There's the exact.
Oh yeah, exact equations. That's right. And then there's also series solutions to differential equations, which is why we have to talk about series at the end of this class. I don't know if our differential equations class actually addresses series solutions, but maybe it does.
I don't remember seeing any questions during tutoring on it.
That have series solutions. Yeah, that might actually be like a differential equations 2 class or something like that. I don't know. I think I remember seeing it when I took the class, though.
Yeah, it was in my course.
Yeah, it might be up to the instructor or something. Okay, so anyway, how do we solve this? Well, separation of variables is pretty much what it says. We're just going to separate the variables so that every occurrence of p and dp is on the same side of the equation. So we're actually going to treat this as a fraction. It looks like a fraction. Leibniz notation is it's not really a fraction, but we can totally treat it like a fraction. And so that's what we're going to do. We're going to treat this dt as like a separate variable. I'm going to multiply both sides by dt. So I'm going to get this. Just multiply both sides by dt. And then I'm going to divide both sides by p. So I'm going to get dp over p is equal to k dt. Everybody see what I did there? It's just a bit of algebra, treating that dp dt as a fraction. Well, at this point, what you kind of see is that this looks like almost like an integral. And it really could be very easily made into an integral by simply doing that. So that's what we can do. We can just put the integration symbol in front of both sides of this. And sure enough, we actually have an integral on the left side with a dp and a p. And on the right side, we have another integral with just a dt. That's it. That's pretty easy to integrate. And so now we actually just integrate both sides with respect to whatever variable we see. So in this case, the left side, we have a p. What's the integral of dp over p? Integral dp over p, what would that be? ln p, exactly. ln p. And I'm not going to put the absolute value around it because in this case, we're assuming, probably rightly so, that we can't have negative population, right? So that's a pretty good assumption. So we'll just drop those absolute value bars. On the other side, we just have integral dt. Well, that is just t, right? The antiderivative of 1 really is just whatever variable you're talking about. So we're just going to have a kt there. Now, we also have to always include our constants of integration. And I'm going to call that one C1, actually. Now, you might be asking, well, wait, there's a constant of integration on the other side too, right? And that's true, there is. There are constants of integration on both sides. However, since they are simply just constants, what we do is just say, well, we don't really need to have two different constants here. Let's just take the constant on the left and put it over to the right, and then we'll just call that a single constant. And you can always do that. If you have any constant in your answer, you can always just sort of absorb it into whatever constant of integration you have. So that's why we only put it on one side. Now, what the goal here is to actually solve this for p. I'm trying to find a function p of t. This is the dependent variable is p, dependent variable is p, independent variable is t. I need a function that has p as its dependent and t as its independent variable. So I need to solve this for p. How do I do that? Well, exponentiate. Put e as the base of both sides. That will cancel that ln, and then you're left with p by itself is equal to e to the power of kt plus c1. Now on the right side, notice, well, we just remember our properties of exponents here. If I have e to the power of m plus n, remember what that is, or how that can be written. That can be written as e to the m times e to the n, right? That's a property of exponents. And so what we can do here is say p is equal to e to the power of kt times e to the power of c1, okay, just by that property of exponents. Then we can, since this is itself just some other constant, anytime you have a constant, that constant can only be determined by further information in the problem. So it doesn't really matter what you call it. We don't have to call it e to the c1. We can say, let's just define a new constant. Let's just call it c. C is equal to e to the power of c1. Again, it's just a constant, so we can just call it that. After that, then what do you get? You get p is equal to c e to the kt. And you can see that is in fact the same solution that they gave us up here and said this is a solution, right? There it is. P of t is equal to c e to the kt. So there we go. We derived the solution. We solved this differential equation using this technique, separation of variables. Okay, now a couple of questions you might be thinking about here. I'll anticipate a couple questions here. How do we figure out what c is? And how do we figure out what k is? Well, there's two answers to that. K is actually dependent on the population itself. That's like an intrinsic property of a particular population. Obviously, populations don't grow at the same rate, right? If you're talking about rate of growth of bacteria in a petri dish, that's much faster, obviously, than like rate of growth of elephant populations, right? Elephants take a lot longer for their populations to grow than bacteria, right? And so that K value would be different depending on what type of population you're talking about. That would depend on the population itself. This C value, that other constant, that would come from like if you know what the starting population is, that C value would in fact be the starting population. Okay, so suppose you start with 100 bacteria, then C would be 100. Okay, so K is like depends on what kind of thing you're talking about, how fast it's actually going to grow. C is really just the starting population. So two different constants. All right, so that's that. Again, we'll see more of this separation of variables concept in the next section, but that's a pretty good intro to it. Now, the assumption that we made on that to get that particular differential equation, just one assumption, that was it. The rate of growth of a population is proportional to the size of the population. Is that a reasonable assumption to just stick with? Like, should we just say, well, that's just going to happen forever, right? Is it true that the rate of growth of a population is always proportional to the size of the population? Or are there other things that we might have to consider? Yeah, clearly not. There's definitely other stuff we have to consider, right? And so what other things, for example, might we have to consider? Yeah, exactly. How much room do these populations have to grow? Resources, exactly. How many resources do they have? Typically, if you throw that other assumption in there, well, you have to alter your model, right? You have to alter the model. And so the other assumption that we make, or if we want to make that assumption that, once the population starts using too many of its resources, its rate of growth is going to slow down, right? And then you might also want to, well, just to put it out there, what is the other assumption? How would we word it? We could say that that there's a carrying capacity. Yeah, life expectancy is actually sort of that's sort of beyond what we would want to consider for right now. But yeah, I mean, if you wanted to make it even better, yeah, you would do that as well. But for now, just this other one of resources available resources or environment, okay? So the assumption that you would make here is that there is this thing that's called the carrying capacity of the environment, okay? You would assume that it's there. And the carrying capacity would be the population at which, if you go above that, the population is not going to be able to grow anymore. In fact, it's going to have to decline. So basically what you do is you make an assumption that there is this carrying capacity, And then you further assume that if your population goes above that, then its rate of growth has to be negative. It has to start falling. And if you go below that, then it has to keep climbing. Okay, so that's it. That's the other assumption. There's a carrying capacity. Any population above that must result in negative growth. Any population below that must result in positive growth. And so making that assumption, and without going into too much detail about how we arrive at this particular model, I'll at least show you why it's going to do everything that we need it to do as far as the assumption that I just tried to explain there. This is it. This is, if you throw that other assumption in there, this is the model that you get. And M is that thing that we're calling the carrying capacity. And it's sometimes called the carrying capacity of the environment. So let's just see, does this really actually do what we want it to do? Does this model what I was trying to explain? Well, notice that, notice what happens if P, the population, is greater than the carrying capacity. Does it result in negative growth, like I was trying to say? Well, if you look at it, I think you'll see that it does, because look, if P is greater than M, then what do we have here? We've got 1 minus something that's bigger than 1, right? A number, well, actually, let's just do it like this. If P is bigger than M, right? P is bigger than M, then look what happens to that thing, right? P is bigger than M, then that number, P over M, is bigger than 1, right? In fact, to make this even simpler, I could just say this is going to be a negative number, right? P, Kp times a negative number. Well, the fact that it is negative, that makes the entire right side of this equation negative, right? But the left side is telling us what? The left side is the rate of change, right? So if the right side is negative, then the left side is negative. And what does it mean for the derivative to be negative? It means that the population is going to be declining, right? And so this does it, right? This does is what we want it to do for P greater than M, if the population is bigger than the carrying capacity. What about if the population is less than the carrying capacity, but bigger than 0? Well, if the population is less than the carrying capacity, look what happens. Then you get Kp. This quantity in particular, P would be less than M, meaning that P over M would have to be a number less than 1, right? And so 1 minus that number would then be a positive number, right? Positive number. And so that would mean that the left side of the equation would be positive also, which would mean you'd have an increasing population, right? The population would be going up because the rate of change is positive. And you can even take this a little bit further and just say, well, what if P is really close to M but bigger than M? If it's really close but bigger, then this is going to result in a very small negative number, and you'll just have a very slow rate of decay. If P is just very slightly smaller than M, then this would be really close to 1 but smaller than 1, and it would be like very close to 1, or very close to 0, I mean, and then you'd have a very slow growth rate, so the population would have a very slow increase. So the closer that it gets to the carrying capacity, the slower the growth rate actually would be. And then finally, there's another thing to think about here. I haven't considered one case, right? What if P actually equals M? Then what? Well, then look what happens to the right side of the equation. What is it? Well, if P equals M, you get 0, right? Because this thing would just be 1, right? And you'd have 1 minus 1. Well, 1 minus 1 is 0. That means the entire right side of the equation would be 0. And then that would mean dp dt is equal to 0. Well, what happens when the derivative is 0? You just have a constant population, right? Constant population. And so that, in fact, is called an equilibrium solution to a differential equation. That is, if the population is exactly at the carrying capacity, you won't have any growth and you won't have any decay. And so it just remains constant for all time. Of course, that's not what really happens in real life, because in fact, that's what's called usually an unstable equilibrium solution. Unstable equilibrium means that if you deviate away from it a tiny bit, it's going to go further away from it. It may not actually be unstable. It would be maybe semi-stable or something like that. No, actually, I'm sorry. No, that would be a stable solution. But realistically speaking, populations don't really do that. They don't just stay the same for all time, right? And in fact, we actually have another equilibrium solution on this as well, right? What's another equilibrium solution? Not just the carrying capacity, but suppose you started out with nothing to begin with, right? Suppose that P was 0 to begin with. Well, if P is 0 to begin with, then there's no way it can grow because there's nothing to reproduce, right? And so that's another equilibrium solution. All right, so in fact, you can glean a lot from a differential equation just by looking at the differential equation itself and not actually solving it. So notice we haven't even solved this thing. All we're doing is just looking at the differential equation itself. And we're able to get all this information about it. In fact, we could even think about what a solution curve would look like without even knowing what the solution itself actually is. And you could think about what it would look like. If this is the carrying capacity, M, suppose you start with a population that's here, below the carrying capacity. Well, right away, what you're going to expect is that the rate of growth is fairly quick because it's significantly lower than the carrying capacity. So it would probably start out growing fairly quickly. But then as you get closer to that equilibrium solution, you'd see that the right side would get closer and closer to 0, but still be positive. And so you would see a curve that looks something like that. Then suppose that you had a solution that was, or a starting value that was bigger than the equilibrium, the carrying capacity. Suppose I had a population that started out up here. Well, then I'm bigger than the carrying capacity, so I should expect a negative growth. The derivative is negative, so I should be decreasing. Again, pretty quickly at first, but then sort of petering off towards that equilibrium solution as time goes by. Okay, so that's kind of what the solution curves themselves would actually look like. And again, increasing at a decreasing rate. Yeah, that would be a good way to say that, right? If you're down here, it's increasing at a decreasing rate. That's right. And if you're up here, then it's decreasing at an, wait, what would that be? Decreasing at an increasing rate. Is that right? I don't even know how to say that. No, it'd be decreasing at a decreasing rate also. But again, you can kind of see that the solutions themselves actually depend on where you start, right? So the initial value is actually very important here. If you have an initial value that starts out above the carrying capacity, then you're going to have a different sort of shape of solution than if you have a solution or a curve an initial value that starts out below the carrying capacity. Okay, so the starting value is very important here. And in fact, when you see all solutions, no matter where they begin, converging like they are here, you see that they're all sort of, no matter where I start, they're all going to head towards this dotted line here. That means that this is actually called a stable equilibrium. M itself is a stable, if all solutions tend towards that equilibrium solution. Guess what happens if you see something like this, where you have your M value here, you start here, and suppose that your solutions all do this, head away from that line. If you see that this line would then be called an unstable equilibrium. I could talk about this all day, but this is not a differential equations class, so so we probably shouldn't go on too long about this, but it is pretty cool. All right, let's try to do let's do an example of it. Go back to just the concept of the differential equation rather than talking about these models anymore. So let's go ahead and let's read through this thing about the general differential equations. So this is not modeling anymore. This is just like, what is a differential equation? A differential equation is an equation that contains an unknown function and one or more of its derivatives. The order of a differential equation is the order of the highest derivative that occurs in the equation. So in other words, if you see a second derivative in your differential equation, so just for example, suppose I give you a differential equation like this. Right? That is a differential equation. The function is y, its first derivative is y prime, its second derivative is y double prime. That's a second order differential equation because it has a second derivative in it, okay? This is just terminology right now. A function f, notice again, it says a function is called a solution if the equation is satisfied when y and its derivatives are substituted into the equation, okay? And I think I've already mentioned that. So now this one's a little bit more involved to show that this thing is a solution. So let's try it. Because this is important to understand what it means to be a solution, how you actually would verify that something is a solution to a differential equation. Okay, so here is the differential equation. Y prime plus 2y equals 2 e to the x. And when we see it's kind of hidden in there, but what that's telling us is that we must view that y is a function of x. Okay, y has to be viewed as a function of x. This might be familiar to when you were talking about implicit differentiation. You had to do the same thing in that case here, or there. We're doing it again here. So now we're actually saying what the solution actually is. We're saying that y is equal to 2/3 e to the x plus e to the minus 2x. Okay, now I'm just claiming that this is a solution, okay? How do we verify that it actually is a solution? Okay, so again, you can see what we have to do. We have to plug it in. So let's look at the left-hand side and the right-hand side separately. The left-hand side is y prime plus 2y, right? Well, y prime means we have to find y prime and plug it in there. So let's find y prime. Y prime is the derivative, so 2/3 e to the x. Now remember the derivative of e to the minus 2x, you're going to have to use the chain rule there. It's minus 2 e to the minus 2x. Then, I keep losing that. Yeah, so there it is. There's the derivative, okay? And so now I'm going to just plug this in. So y prime. I'm going to plug it in there. 2/3 e to the x minus 2 e to the minus 2x. Okay, so just to be clear, this is y prime. And then I still have to plug in plus 2y. Okay, well, 2y, what's that? It's 2 times 2/3 e to the x plus e to the minus 2x. Okay, so everybody see that? Plus 2y. That's what all this is. Okay, y prime plus 2y. So that's the left side of the equation, right? Now on the right side, I don't have to really do anything because it's simple already, right? The right-hand side of the equation is just 2e to the x. So what I need to do now is just verify that what I get on the left side is going to equal what I get on the right side. Okay, so that means I need to simplify this left side and just make sure that it simplifies to 2e to the x. So let's see, does it do that? So we got 2/3 e to the x minus 2e to the minus 2x. Let's distribute that plus 2, so plus 4/3 e to the x. Distribute the 2 to the second term, we get 2e to the 2x to the minus 2x. Okay, so what do we have here? We've got 2/3 plus 4/3, right? That's 6/3, right? So that's 2 e to the x. And then look what we have here. Minus this plus this. Those cancel, don't they? And so what am I left with on the left side? 2 e to the x. What do I have on the right side? 2 e to the x. These are equal, right? So we have just verified that this is a solution. So y does solve the differential equation. Now, in this case, of course, we didn't solve this differential equation. All we did is just figure out what the solution is. Or we figured out that the thing that they claim the solution is actually the solution. All right, so now, if you did want to solve this differential equation, this is not separable. This is not one that we could solve by separation of variables. So we couldn't, in this class, we couldn't do it. In fact, this is called a non-homogeneous first order ordinary linear differential equation. So there's all these little adjectives that you can add to differential equations. First order because it's got a first derivative. Linear because these terms here are all just, they're not squared or anything like that. non-homogeneous. A homogeneous differential equation is a differential equation that's set equal to 0. This is not 0, so that makes it non-homogeneous. And it's ordinary, the class that you're referring to, ordinary differential equations. The other type of differential equation besides ordinary is a partial differential equation. And those involve not regular derivatives, but partial derivatives. Partial derivatives is something that you don't see until calculus 3. That's three-dimensional stuff. So partial differential equations, if you ever want to take a really hard math class, as an undergraduate, I took that class. That was the hardest undergraduate math class I took. Honestly, it was a bear of a class. I didn't even get an A. I only managed to pull a B in that one. That was a tough class. So if you go on and take, higher math, I think that's like senior level math class. So partial differential equations. All right, so let's see. Example 2. Yeah, this one is just kind of, I'm not interested in that, huh? Don't want to try that. Yeah, partial derivatives are like if you have a function of more than one variable, like f of x, y, or f of x, y, z, something like that. So you have a partial derivative, you differentiate with only one of those variables. Yeah, you'll see that all in calculus 3. All right, so here again, we're just going to kind of look at the what the differential equation itself tells us about the solutions. Even if we can't find the solutions, we can at least tell a lot about what's happening just by looking at the differential equation itself. And so that's what we're going to look at here. For what values of p is the population increasing? Okay, so this is kind of, oops, that should be a minus, not a plus. So this is kind of what I was talking about before with that carrying capacity situation. In this case, it's not quite the same because we have that p there as well, so not exactly. Oh no, I guess the p is supposed to be, yeah, so this would be like a logistic growth model. So what is the carrying capacity here? Of all the numbers that we get, 4,200, right? 4,200 is the carrying capacity itself. And so this shouldn't take too much. For what values of p is the population increasing? What would we say there? For increasing population, what would we want to see? P should be less than that, exactly. P should be less than that. Yep. So that's all we need to do is just answer that question. For what values is it decreasing? Yeah, just P greater than that. That's it. Everybody see why that's the case? Why this is what everybody's looking at here? It's really that term right there is what's happening. If P is greater than 4,200, then this number that I've circled is bigger than 1. And so that means we're going to have 1 minus a number bigger than 1. That's going to make this side negative, and so that's going to result in decreasing population. If that P is less than 4,200, right, then this is going to be a number less than 1. 1 minus a number less than 1 is a positive number. Left-hand side is positive. It's going to be growing. And then what are the equilibrium solutions? There's 2 of them. I think we've already seen P equals 4,200 is 1, and the other one would be 0, yeah. Yep, 0 and 4,200. Those are the 2 equilibrium solutions. So if you start with either of those equilibrium solutions, the solution to the differential equation is very simple. It's just remains either 0 forever or it remains 4,200 forever. Okay, so these are the problems to work on now. That first one is just verification. So just you would look at the lefts, you would see what derivatives you need to take. It looks like you need to take the first derivative. That's it. And then you see the y in there. So what you're going to do is like what I did. Left-hand side, t dy dt. So take t multiplied by the derivative. Sort of simplify that as much as you can. Separately, this is kind of like verifying trig identities, if you guys remember that. You look at the left side, you simplify it as much as you can, leave it alone. Look at the right side, simplify it as much as you can, leave it alone. At the very end, what should you expect to see? You should expect to see equality. That's what you're going to do here too. Figure out the left side, simplify it as much as you can, leave it alone. go to the right side, simplify it as much as it can. At the very end of those two things, you should see equality, right? A true state. Now, this is actually called an initial value problem. So problem 1, when you see that word initial value problem, those words, that just means it's like a combination. It's a differential equation combined with an initial value. Okay, those two things together. When you have an initial value problem, you have to verify two things. You have to verify the differential equation itself is true, and you also have to verify that the initial value holds. So in that case, that's really simple. All you got to do there is just verify that when you plug pi into this function, you do get 0. So that should be easy. Just plug in pi, make sure you get 0. And then for the differential equation, just do what I said earlier. For problem 2, this is a good one because it kind of gives you a hint about how you would determine the solution to this type of second order homogeneous differential equation by the method of the, is that the undetermined coefficient, or is that, yeah, that's undetermined coefficient, because we're wondering what those coefficients would be. So for that one, number 2, see if you can figure that out. You're just trying to figure out what values of r would satisfy that. And then we arrive at a really cool conclusion in part B there. It's called the principle of superposition. I'll talk about that when we talk about this problem. Problem 3 is another one of those sort of just conceptual examples. And then problem 4 is a good question about Newton's law of cooling. See if you can figure these out. At least for now, just try to at least verify that that solution on number 1 is really a solution. And if you have time, move on to the rest of these. So I'll give you a few minutes again to work on that stuff, and then I'll come back and we'll go through them. And I've got Michael's solutions here, so I'll just post them up here. Okay, so what Michael's done here is taken the derivative first, right? That's this. The derivative of the function. That's necessary because we have to plug that in. That's the y prime part, or the dy dt part. And then he's just done both. The left side is t times the derivative. So there's the t, there's the derivative. Okay, so plug in t, plug in the derivative, and simplify it. And this is what you get when you do that on the left side. Okay. On the right side, what does it say? It says y. So this is the y. This is the y. And then it says t squared sine t. And so obviously that just stays as it. That's the t squared sine t. And so if you simplify the left side, you see that indeed you get the exact same thing that you see on the right side. And so again, this is kind of like a trig, verifying a trig identity. Do you get equality after you simplify both the left side and the right side? And we do here. So that means this is a solution to the differential equation. So the second one is saying find the values of r, basically. What values of r will satisfy this differential equation? So what we do, start out with just this function here, y equals e to the power of rx. Okay, and then we're actually going to plug that into the differential equation, that and its first and second derivative. So the first derivative, again, by the chain rule, y prime is equal to that. It's the chain rule. You got to put that r there. Y double prime, another application of the chain rule, you get the r squared. Okay, and so what Michael does next is he plugs in twice the second derivative, 2 times the second derivative. So that's this. That's the 2y double prime. And then plus the first derivative. Okay, so there's plus that's the y prime. And then minus the function itself, minus the y. So that's minus the y right there. Okay, so plug it into the differential equation, the first and the second derivative. And then notice that when you do that, all of those terms have that e to the rx. And so you can factor it out. Well, what does that leave you with? That leaves you with this quadratic equation. You see that? Quadratic equation. 2r squared plus r minus 1 equals 0. And so you can solve that, right? You set it equal to 0, and actually you would set both equal to 0. The e to the rx is equal to 0 also, but that has no solution. There's no value of x that will make that 0. The other part of it, 2r squared plus r minus 1, does have 2 solutions, right? If you solve it, you get this and you get this. So that's it. That's what that solves this, or that verifies that Actually, it does more than verify. It tells us the R values that satisfy this differential equation. And in fact, this method here that we're doing is called the method of the undetermined coefficient because we don't know what the coefficients are. And the way that method actually works when you take differential equations is you basically just say, well, I'm just going to guess what the solution is. What solution could we possibly hope for where when you take the second derivative and multiply it by 2 and add it to the first derivative and then subtract the original function, what possible function could you get that when you do those things, you actually get 0? Well, it has to be a function whose first and second derivatives look an awful lot like the function itself, right? In fact, there's only this e, an exponential function, is one of the only functions that has that property, where you take multiple derivatives and you keep kind of getting the same function back that maybe just differs by a constant, right? And so it's a safe assumption that our solution is probably an exponential function. And so what we just do here is just assume that it is and say, okay, well, if it is an exponential function, what should be multiplied by those x's? What should those r values be? And so, in fact, this is a perfectly valid technique of solving differential equations. You just guess the solution and then plug it in and see if it works. If it does, then it will also tell you what these values of r should actually be. So there's that. And then for part B, it says show that if you take both of the solutions that we got, in other words, we got e to the power of 1/2 x, and you got e to the power of negative x. Those are the two r values that we got, -1 and 1/2. If you multiply those by constants, in other words, an a and a b here, and then you also add them together, right? In fact, when you do this, when you take two different solutions and you multiply them by random constants, a and b in this case, and add them together, this is what's called a linear combination of the two solutions. This is a linear combination of the two solutions. Linear combination. And it turns out that there's this principle it's called principle of superposition. Actually quite an amazing result. It says that if you can find two solutions to a second order differential equation, then you can take any linear combination of those two solutions, and that will itself be a solution to the differential equation. Okay, so in other words, this thing that's here, this whole thing, must also be a solution to the differential equation. And that goes for any a and b there, in fact. It could be any a and any b. And so what Michael does next is actually plugs that into the differential equation, right? It's 2y prime, or y double prime, I mean, so you have to actually take the second derivative of this thing. That's the second derivative. That's the first. So 2y double prime, that's this, 2y double prime. Again, I'm just plugging it back up into here. Or Michael is anyway, plugging it back up into, that's 2y prime plus y prime, so there's the y prime, minus y, and that's the function itself. Okay, so you see second derivative here, this is y double prime. First derivative here, that's y prime. Function itself here. In fact, that's 2y prime there. 2y prime minus y prime minus y. And then simplify all that craziness. I mean, you do get a pretty big mess of stuff here, right? All of this. But once you simplify all that, look what happens. There's the plus 1/2 a e to the 1/2 x. And then there's plus another 1/2 there, right? This one and this one add up to be one of those. But then look what happens later on. There's a minus, the same thing, right? So those two cancel with that. And then look what you have here. 2b to the minus x, and then there's a minus 1 there, and there's a minus another one there. So that 2 cancels with that, and what do you get? You get 0 equals 0, right? And so sure enough, that linear combination of those two solutions is itself a solution. And again, that's called the principle of superposition, if you're interested in that. You will definitely see that in your differential equations class. So basically what that's telling you is that if you want to find the most general possible solution to a differential equation, all you got to do is find two solutions, so-called particular solutions. And then you make them into a linear combination, combine them together by adding them and multiplying them by constants, and then that itself will be the most general solution to the differential equation. So pretty cool. All right, then for number 3, again, this is sort of just a visual sort of thing here. In fact, I think on that one, I'm gonna, yeah, so what are you doing there, Mark? You're just picking points, I guess?
The first part, I made the observation that at the y-intercept, we got x equals 0 and y is some positive number, and saw that there was a positive slope there. So I just went to see whether or not those equations gave a positive slope at that point, and B
Right,
did
okay.
not.
Sure. I think I'm actually going to do this one with a graph real quick, just so everybody's clear on what we're looking at. So let me go ahead and share the whiteboard again and see with the graph, like kind of how this is actually working. Yeah, so just so everybody's clear on, this is like graphically checking, could it possibly be a solution just by looking at the graph. So if the graph does something like this, I'll try to copy this as closely as possible. Could this be a solution to A? Y prime equals 1 plus xy. Well, again, what this differential equation is telling us is the left side is the slope of any solution curve. That is the slope. So what we can do is pick any point any point in the Cartesian coordinate system. If it's in quadrant 1, which most of the solution is, look what happens. If I pick a point, any point in quadrant 1, right? Here's a point in quadrant 1. Well, what's true about any point in quadrant 1? Well, any point in quadrant 1 is going to have both x and y be positive, right? And so if I have a point in, right, they're all positive, right? If I have x and y both being positive, then what has to be true about this right side? It can only be greater than 0, right? If I plug in any point in quadrant 1, right? And so what Michael was saying is that, okay, well, let's pick a point that's even just quadrantal, right? That's right there on the y-axis. If I pick that point, for example, that's got an x equals 0, y equals 1. It's got a positive slope, so that seems to work. But look what happens over here. Any other point in quadrant 1 that moves to too big of an x value, look what you got there. You got negative slopes, right? So there's no way that if you plug in positive values for x and y, that you can possibly have a negative slope over here, right? That just doesn't match. So this cannot be the differential equation that produces that particular solution curve. So let's try the second one. Could this be it? Well, now again, if you think about any point in quadrant 1, well, again, they're all positive. And so if I pick any point in quadrant 1, this seems like it might work because it's going to produce all negative solutions and thus all negative slopes. However, we do have this problem that's just a little bit to the right, like right there, right? Right at the x-axis, or even just a little bit to the right of it. What's going to happen there? You have positive slopes there, right? There's some little bits there where you do have positive slopes. And so there's no way that this could possibly produce that solution curve because there are a few little points in quadrant 1 where you do have positive slopes. You guys see what I'm talking about? Well, by process of elimination, that means it has to be C, but let's just verify that that actually does what we want it to do. Now, again, in this case, you can see that most xy pairs will produce a negative solution here, right? Because 1 minus 2 times, if x and y are both bigger than 1, for example, then this is definitely going to end up with a negative. 1 minus a number that's bigger than 2, right? 1 minus something bigger than 2 is going to definitely be a negative value. However, it does also allow for a few x-y pairs where you will have positive slope, right? Suppose x is really small, for example. If x is really small, then that would make this whole thing small enough to be less than 1. And then you got 1 minus a number less than 1. It is going to allow for a few places here where you have these positive slopes. Okay, but for the most part, they're all going to be negative. Like if you pick anything over here, all of those are going to have negative slopes. So this is the one for sure. Part C, that's the solution. That's the one that it has to be. Any questions on this? So that's an important skill to be able to have, to like look at the differential equation without solving it and just seeing what information can you get just from the differential equation itself, not solving it. So let's look at number 4 then. See what you got on number 4 here. Yeah, so for this one, suppose you have just poured a cup of freshly brewed coffee. When do you think the coffee cools most quickly? So, again, just thinking about this, like your own experiences with physics. I'm sure everybody would know the answer to this, right? When does the coffee cool the most quickly? Well, probably right after you pour it, right? When it's the hottest, that's when it's cooling the fastest. And then as the coffee cools down, the rate of cooling slows down. Right? So if you were to kind of graph it, you'd see that graph that you see that Michael has drawn there, sort of quickly dropping off right away, and then sort of getting leveling off as time goes by. And then Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings. Okay, so that sentence right there itself produces a differential equation. And look, you can go word by word on this. The rate of cooling, right? Okay, the rate of cooling, that means the rate of the change of the temperature with respect to time. That's what this is. Big T, capital T is temperature. Small t is time. That dt means rate of change of temperature with respect to time. Is equals proportional to. Okay, well, proportional to puts the k there, just like it did on the population one. That's constant of proportionality. Well, what is it proportional to? It's proportional to the difference between the, what does it say? Object and its surroundings, okay? Well, TR, I guess TR, is that what you're calling the,
Yeah.
oh, yeah, temperature of the room, there you go. TR is the temperature of the room. And when it says the difference between the temperature and its surroundings, I think, Michael, you have that reversed. It should be T minus T sub R.
What I did with this one,
it doesn't matter too much.
I made it so assumed K was positive. So when I put it in this order, it forces the negative sign to get the temperature to drop.
That's right. Good. Okay, I see what you're saying. Yeah, so he's assuming K is positive, so we want that value to certainly be negative because we want the temperature to be dropping. We want negative slopes there. Okay, so perfect. Yeah, that's great. And then, yeah, so the difference between just means subtract one from the other. And so there it is. That's the differential equation that models Newton's law of cooling. Okay. If you made the assumption that K was less than 0, then you would flip that T minus T sub R. And then, let's see, what else do we have here? What is the initial condition? Okay, well, here's the initial condition. What is the initial temperature of the coffee? There it is, 95 degrees. And then, does in the view of your answer, does this differential equation, is this an appropriate model? And I think it perfectly is, because the closer that T gets to T sub R, the closer that this whole thing in parentheses is going to be to 0, right? And that means you're going to have a very slow rate of change, and that's what we're seeing here in this tail end there, right? Temperature is changing very slowly right there, because we have a very small difference between the temperature of the object and its surroundings. But right away, when the temperature difference is big, we should expect a larger negative value, and that's why we see steeper negative slopes right there. Now, there's one other thing that I should point out there. Why do they say provided that the temperature difference is not too large? Why does that have to be an assumption as well? What happens if the temperature difference is too large? Well, that would be a weird situation, right? I mean, your coffee would have to be like, I don't know, 1,000 degrees or something like that. But if coffee was really hot, like 1,000 degrees, what's going to start? Yeah, then the surroundings themselves are going to start changing. The coffee will actually then change the temperature of everything around it rather than the stuff around it changing the temperature of the coffee. So if it's too hot, it sort of reverses things, right? Then the coffee is doing the changing rather than the other way around.